So please put your hands together and welcome Tim. Sorry, it's just on the table behind you. Perfect.
Hello everyone, my name is Tim and welcome to a series of talks held by me and my colleagues from the same company called Avito. Avito is a service that connects buyers and sellers of different stuff. It's similar to Craigslist and OLX, but has 35 million unique active users per month and quite complex mobile applications, each having more than 1,500,000 lines of code. And today we're going to talk about the startup time, which is an important metric because it forms the initial sense of your application. So let's take a look at this timeline and split it into two eras, before main function and after main function. In the era of after main function, we take the time profiler and do our best to just do minimum work at the start and postpone everything to the later days. So you should be lazy, do not create tabs on tab bar controller or something like that, or labels if you don't present any content. And do not even use background threads because you really want your CPU to be free for main thread execution. So that's basically the three main points of after main. And before main, we can realize what's going on using duality print statistics environment variable, which in most of the modern projects shows that dynamic libraries loading is the main issue. And why is that? Just because there are lots of those dynamic libraries in those applications. So this brings us to the question of the talk, how to reduce dynamic libraries count. And actually there are two main approaches to this. Option one is CocoaPods plugin called AmiMano. It's open source and available on GitHub. It even has a logo type, so yes, it's a real technology. And we've been using it for 2 years quite extensively, and it works fine. So what does it do in a nutshell? We have two applications and dynamic frameworks bundled inside. And now on the right, we have the application with AmiMano involved, which shows us that we have no dynamic frameworks at all. Instead, we have binaries of those dynamic frameworks linked statically. So yes, AmiMano links dynamic frameworks statically, and that was my face when I initially heard about that stuff. We've been using AmiMano for 2 years, quite extensively and successfully, but later came up with another solution, quite an opposite one, which is dynamic libraries loading. Oh, lazy dynamic libraries loading. It's a bit tricky and it requires your application to have a specific architecture. My colleague Vadim will tell you a bit more about this later. So at the bottom we have core layer. It consists of just utility modules like networking, analytics, feature toggles, and so on. Core layer is used by the feature layer, which consists of modules with UI, like messenger feature, newsfeed feature, settings feature, and so on. And features get reused by applications. So even with this architecture, we can lazily link features because they are independent from each other. However, we cannot use this approach to lazily link core layer because the complexity or the dependency picture looks quite complex there. And here we need just this magic cat to merge core layer into a single module. And that's how we reduce dynamic libraries count. Using this approach, we'll get this picture on the application start up. Just one module from core layer, one module from feature layer, and that's all. And later on, we can on demand load these features as we need them. I know what you're going to say, just merge core layer into a single module, no problem, easy peasy, right? But actually that's not an easy peasy task, and it's just beyond this talk because it deserves a different talk, actually. So, we have two quite different approaches. Which one to choose? Let's take this highly theoretical graph which shows startup time depending on the project complexity. And in our project, we managed to realize that AmiMono grows faster than lazy dynamic libs loading. Here's the midpoint, which pinpoints the simple projects from complex projects. In simple projects, AmiMono really shines, and on complex projects, AmiMono loses. We actually won 8% by removing AmiMono and using lazy dynamic libraries count. One more slide. So wrapping things up, AmiMono works best on simple projects. Lazy dynamic libraries loading works best on complex projects, but requires a modular architecture and a tool, magic tool, for merging core layer into a single module. Well, AmiMono is easy to use, so we highly encourage you to try it out. It works best for 99% of projects, and that's all for now. Thanks for listening, and know that you can that you can optimize your upstart time not only on the application layer, but on the system layer as well. Take care.
Perfect. Thank you very much, Tim. Cool. So we're now going to go straight up to Vadim, who is going to continue. So please welcome Vadim.
Hello, everyone. I would like to make lightning talk about dependency injection. First of all, we use an extremely modified version of deep library with IP changes, different optimizations, and additional functionality. A bit of history. Initially, our iOS project was a big monolith, one huge binary. On a slide, you can see a connection between Viper's models. It looks like this. Now you understand full image. And we have some problems with this scheme because the large binary compiled from more than 2,000 of files, and it was very slow because it's compiled only on one core. And we also have some problems with IDE and some conflicts in project files. And the most painful things is the incremental build didn't work. And also we have some strategy for our project. We want that our project should be scalable. We want reuse functionality between applications. Also we want some impact analysis and code ownership. And the main goal is make our developers happy while they work on our project. And the answer is a modularization of our project, and it looks like this. It's a feature, models, mediator, and core layer. And we just split our monolith on these layers. The main rule for receive benefit from parallel compilation is the feature shouldn't depend on each other. And mediator should be lightweight and compile fast. How to feature communicate between each other? For this, we use dependency injections. We have some container, and feature can register implementation and put it on container. Then another feature when want some impl, it get container from mediator and just get impl from container. That's all. And some sample of code. Here we register some service and then just resolve it. It's simple. We use closures here. And about testing. How to test this solution? Here code generation help us because we can be sure that we have full code coverage. You need to activate all registration and resolve, and then check the full compliance for it. Some additional features. It's lazy resolve, lazy register, and a lazy framework load. I'll start with lazy resolve. It works like lazy Swift property in Swift, but has a log for synchronization for multi-threading. It's a simple wrapper. Let's move. Lazy register. We have made a special class that provide case and definitions for finding a factory and finding the instance that can be lazy register and resolved. Let's look on the scheme. We try to resolve something from container. If it's success, we just return it. If not, we find provider by key and then try to load framework. If success, we register all definition from factory and then resolve. If not success, we load framework like in previous presentation and then register it. And also we have some special tool. It's called warming up. After displaying the first content, we call warming up, which load unnecessary at the application start code. And it's reduce time for open another screen. And some advice for make sure that you save. It's be sure that you have a full test coverage. You should have a performance test and metrics. And of course, you should have a real-time monitoring for see that work correctly. That's all.
Brilliant. Thank you very much, Vadim. And we now go on to Vladimir. So please welcome Vladimir.
Hello, everyone. My name is Vladimir, and I want to share you our approach to implementing feature toggle mechanism. So, what is feature toggle? This is a versatile approach on a feature management when each product-related code block is associated with certain feature flag, which is Boolean variable, basically. And this allows us to turn this chunk of code off or on instantly. So let's take a look on a simplified version of our toggle framework. At first, you have to implement a new instance of toggle object. It has only two fields, the title and the value. So how to use it? For example, we want to add some kittens to the main page of our app. We find the best place to store all business logic. Then we check the flag value and unleash the kitten if flag is true. This way, we isolate all logic related to this kitten feature inside the separate logic branch. Unleash method can be unimplemented, can crash, anything. Before you turn on the flag, the code will not be executed in the production. So, all other team can commit their changes independently. And also, what happens if we decide to remove this kitten feature? For example, if it wasn't successful. If this code wasn't isolated, we have to find all feature-related code across all application code base and revert it. And with feature toggle, we just delete this branch, and that's all. And if the feature is successful, we have a clear overview of changes you have to merge with. So we just delete and merge it. So what is the profits? Let's recollect it. It's much more easier to add or revert changes across big teams. This is more isolated and feature-related logic. It's possible to turn off certain feature instantly, and code base is stable and consistent under frequent changes. So this approach have many positive, but there is one big flaw. All toggle values hard-coded inside our app. So the next logic step was make them remote and dynamic. So app used to ask toggle storage for a value and store just a static class with constants. Our team created microservice to provide toggle values to the app. Let's take a look how page for a certain toggles look like. You can see the toggle value and description, versions of app where the toggle exists, and % rollout controller for each version. Also, we have history of changes, like notification upon changes, all this stuff. And of course, we have metrics. We love metrics. So for each feature, we create Grafana dashboard with value distribution. The x-axis is the time, and y is the value distribution in the %. We can see time when we turn on this feature. You can see rise in the graph. And it helps us to monitor the real distribution from real devices. Let's see how our behavior changed in moments of fuck up. Let's pretend our new feature crashes constantly. What should we do in an old-fashioned way? We should turn off feature and merge changes to the master branch. Then we should upload a new version to the App Store. We have to wait for an App Store to review and release our new version, and maybe user will download new version without crash. So this takes a hell lot of time. And this is where remote feature toggle comes in. Now we can turn off feature instantly and user will receive our update at the next start. So that's all for today. Thank you for your attention, and if you have any questions, ask me during the break or online.
Thank you, Vladimir. And finally, we've got Vladislav.
Hello. My name is Vlad. I'm also from Avito, and I work on testing infrastructure. I will tell you today about how we run UI tests and why do we run them. So, first of all, we have a lot of app releases. This is the release schedule for the last 1.5 years. We have like a lot of publishing to the App Store. It's like we publish every 2 weeks, and actually you can see there is a gap right here. It was a January, New Year time. So in Russia, we don't work for 10 days during New Year. That's why we didn't release anything. We've been celebrating quite extensively. So to support this quickly moving release train, we run UI tests, automated UI tests. We run a lot of them, and it's usual to call them native UI tests because it's like touches which is programmatically happening on the simulator. And somebody called them XCUI tests because they are based on XCUI. This is the graph of number of automated tests. See how fast it grows. Cool? But here the graph stops because I don't have any data. But then suddenly I have more data. I don't know why there's a gap, so yeah. Here, we just deleted the failing tests, like forgotten, dusty failing tests. And yes, we have 800 UI tests. Also, we run tests on pull requests. Not all 800, but some of them. Very stable tests are being run on pull requests, about 300. And we run all test suite throughout the day, many, many times. We call that full regression suite, or suite. How do you pronounce that? It's quite massive, right? Because if you multiply 800 tests by 60 seconds, it's the time each test takes on average. You get 13 hours. 13 hours, right? And we run them 3 times, actually. We run them against 3 iOS versions. It's iOS 10, 11, and 12. And it gives you 39 hours. And that only if test fails or passes immediately, like after a single run. But if it fails, you have to retry it because it might be flaky. So it gives you, after all the retries, 41 hours of pure UI testing, right, on the build machine. You can imagine, if you run 41 hours of UI tests on a single Mac, no matter what Mac it is, it might be tired as a Ben Affleck. So we built MC, which is a tool to automatically distribute the test run across many, many Mac machines. This is a nice attention-holding animation. So MC runs both UI and unit tests, which is a nice feature, and it kind of simulator farm on iOS world. It has some prioritization feature as well. So imagine like full regression build takes 1.5 hours to run 800 tests multiplied by 3. But if pull request comes in, we put the full regression on pause. We run UI tests from pull request quickly, and then full regression continues. MC also load balances our Mac machines. So here, each brick is a UI test, and you can see all machines are loaded. They are not idle, which is good. We use TeamCity for continuous integration, and these are the screenshots from the full regression build. Here, the magic numbers are 41 hours of UI tests run in 1 hour and 41 minutes, which is good. MCL has lots of capabilities like plugin support. It's actually very easy to use. It's a single command to start the simulator farm. And support for real devices is coming. We are very interested in adding support on real iPhones and iPads. Thank you for your attention. This is the QR code with all the 3 links. You just scan it and it will open the paste bin. Take care.